Okay, hello everybody. Welcome to AP Physics today. We're going to talk about power, which is our last section in this chapter. So it's just practice, practice, practice. After that, the first thing I want to talk about though is work. So if we talk about this, we talk about moving a box. So let's say we have a 10 kilogram box and we take our hand and move it over a height of 10 meters. Could you tell me how much work was done? Well, change in potential equals the work that, now when I say work in this case I'm talking about the work that you did, not the total network. So it'd be mgh equals work, right? So it'd be 1,000 joules is the work done. Do you agree with that? Okay, so let's say that Hercules comes by and says, hey, I can lift that box the same height because he's trying to get a job at the time. He hasn't been working for a while. So I wanted to do some work. He said, I can lift that box and I can do the same amount of work, but I can do it faster. Okay? So if I do it faster, am I going to get more work done at the end of the day? Yeah. So the word power then is describing the difference between these two. Because if we just use work, they're doing the same amount of work, but if someone does it faster, then we say they're more powerful. So the physics definition of power then is the rate of work, or work per time. So back in medieval times, when they were plowing the fields, do you know what they used to plow the fields with? It was oxen, very good. And the oxen, anatomically, so here's a tie into biology, the oxen's shoulders are ahead of their trachea. So if you got like an oxen here, that's kind of what an oxen looks like. Would you say? This isn't a very good picture, but there's a T-bar that goes between two oxen and then goes through the plow. Do you know what I'm talking about? Have you ever seen that? And that was cool because these oxen then could, and then the plow is attached. I'm not having a very good day of drawing, but you know, this is what the plow looks like, right? And it was somehow attached to that T-bar, and then there's a guy steering it with the handles, and then it would like rip up the earth there, and you could put seed in it and plow, or in it, and then plant, right? Okay, so this guy though said, hey, I've got something else, a new animal, he said. So this guy said, hey, it's taking you too long of a time to get the field plowed because I need to put seed in there before it rains so we can have something to eat in a few months, right? So this guy came along and said, hey, I got something new. You know what he said? He said, I got one of these. So you can tell what this is for sure, right? This here is a better picture. A gooder picture.
It's a camel.
We got a horse, right? And so they put that T-bar on the horse. You know, there's another horse back here. You can probably tell. What was the problem with the T-bar on the horse?
Squish the trachea.
Exactly, it collapsed the trachea. So like the horse was, why was the horse better than the oxen in the first place?
It's faster.
Yeah, like Seabiscuit, right? Can run. Where oxen, if they run, I don't know what happens. They might fall down. But horses can run, and so they're going to do the work faster, which means they're more powerful. Okay, so hopefully you remember that. That's what we're talking about. Speed of getting work done. So, that didn't really work because horses were dying, or at least choking. And And then the work didn't get done anyway. So then, what was like the second industrial revolution?
The solar thing.
Yeah, it looks kind of like this, right?
Or
The horse collar. And this little area down here, so the horse goes like this, right? This little area here was extended around where the trachea was, and so it would put the pressure back on the shoulders of the horse, where the oxen didn't have to do that because they were different that way anatomically. And so once the horse collar was developed, then we could farm a lot more. So in your history books, it doesn't call this an industrial revolution, but in reality, it might actually be an industrial revolution, the horse collar. Got more work done, you could feed more people. So as you can tell in the notes, then power here, this is the actual AP equation. Power is work per time. You see it written on the board right over here. Power is work per time. And watt is something we don't really use at this point. Watt is something we use. Horsepower is not something we use. But watt is the official unit for power. And it's joules per second. So joules of energy per second. So power is work per time. You could plug and chug that pretty easily, right? Okay, so let's go to the next page of notes. If you look at power, and then also have all this on there too. So if you look at power formula, being work per time, you can also say then power is force parallel to displacement per time. Do you agree with that? Okay, so this is, probably going to be more useful to you than this form, but of course for the same thing. But let's say that you're pushing on something here. So let's say that I'm putting a Newton or a force of, 10 newtons. Is that object going to move if that is... How is that object going to move if it has initial velocity that's not equal to 0, and I have a frictional force on it equal to 10 newtons? How is that going to move? Constant, right? A constant velocity. Okay, so let's analyze this. This thing is going to be going at a constant velocity, right? So how does that work into power? So let's say our velocity is constant. And what is the unit label for velocity? Meters per second, right? Okay. And work is defined as force parallel to displacement, or we could say force times x, right? And the label for x usually is newtons times, what's the label for x? Meters, right? Okay. So if power then is work per time, and work is force times displacement per time, could we figure out how much power we had in this formula if I gave you, let's just say I gave you 7 meters per second? Could you figure out how much power was wrapped up into moving this box? How could you, Tyler? Okay, so the question is, well, we don't have time here, right? But power is a rate, which is, in this case, work per time. What else is a rate here? Well, this is a rate, right? Because we go 7 meters per second. Okay? If you're thinking of power as force times displacement, ask yourself, what is meters? So if we look like this, at this right here, what is d over t? D over t labels would be, force is equal to m in label form, or not force is equal to m, but force times d over t would can be rewritten as m over s, right? Or you could say m over s is what? V, right? So power can equal force times parallel velocity. And that's our second formula that you get for power. Any questions? Okay, so here are our two formulas. Work per time or force parallel velocity, which they're actually, the same thing if you do unit labels. So, should we figure this out? Should we do a couple examples? Okay. So let's say that you take a box and you move it. Let's say that we have an angle of 30 degrees, and you move it 8 meters up, and it takes about, let's say it takes 2 seconds. Okay, so my question to you then is, how much power was shown in this example? Okay, so the question is there a force? Well, yeah, because mg is here.
How's it traveling?
So mg divided by 2 is the force on the ramp.
I thought it was going up because the arrow.
This is a frictionless ramp, you're right, and I'm glad you mentioned that. I did have to tell you, this was a frictionless ramp, but we almost always start out with frictionless stuff because that just slows us down otherwise. So, power equals work per time. Power equals force parallel displacement per time. Power equals mg divided by 2 times 8 divided by 2. So power then equals 8 mg. Do you agree? The actual answer is 2 mg or 20 m. Okay, so that's powerful. Is there another way to do this, though, is the question. Which is more important, I think. Yes, okay, very good. So could you say that power is, in this case, change in energy per time? Yes, you could. And, the whole thing is I didn't say that either this is a constant velocity or the initial and final velocity are both 0. But if we go power, change in energy is change in potential this time, right? Divided by time. So we can do mgh divided by time. Well, it's delta h, really. Right? So power, in this case, then would be mg, what would we have here? The sine of 30 times 8 divided by 2. And we should get the same number. Check it. And it works out to the right answer, 2 mg, or 20 m. Okay. Well, let's do another problem. Since we're on the ramp, we might as well stick with it. Let's say that we have 30 degrees again. Let's say that we have m1. Let's say that our v sub naught equals 0, and let's say that our v equals 5. And we'll say that our distance that is moved is 10. And we'll say that the time that it took for this to happen is 4 seconds. I want to know the power for this. So if we think about change in energy per time, then we can say power in this case is change in potential plus change in kinetic divided by time. You agree? So power here is mg, and our change in h is, well, it's going to be 5, right? Or the sine of 30 times 10 plus 1/2 m, and we had a v here, right? Times 25, all divided by 4, and the power of this then is 15.625 m is your power. Okay? So are you understanding this relationship between work, energy, and power? So the question was, well, geez, why can't we do this? Well, we can, but this would be better written as average velocity. So in this case, power would be force parallel to, 5 divided by 2. Do you agree? Okay, now the force, though, I'm not sure if we can figure that out real easily or not. So we'll see if we can work this out. I don't know. There's a force down the ramp, right? And that's going to be sine theta mg. If I was forcing with just that, the thing would move, right? But there's also, so I've got to force this much plus whatever is going to cause, this force is going to cause the acceleration of the system. So acceleration of the system then would be the square root of 2, it's v squared divided by 2x if you use the kinematic equation. V squared divided by 2x. I might be screwing up here, so stick with me on this. We got 25. Do we have displacement here? Divided by 20. So acceleration of the system then is 1.25 meters per second squared. So let's just see if this works, because I know that is right. And then we'd have to plug that into our force equation here. That would be force is mass times acceleration. So force is m1 times 1.25. Okay, and that force plus this force would give us our power. So if we look at power equals 1.25 m1, and the sine of theta in this case is 30, so that's 1/2 mg, right? Plus 1/2 mg. That would be our force. And our average velocity would be 5/2. So let's see if you can get the same numbers that way. And using 10 for g, we do end up getting the same numbers. So yes, you were thinking right, but you didn't realize it was average velocity. Okay, so we got to bring Newton's laws back. So we're going to talk about a Wookiee. You know what a Wookiee is, right?
No.
Okay, so the Wookiee runs up the hill. Okay, and the Wookiee runs 100 meters. The hill is 30 degrees, and it takes him 5 seconds to do so. The question is, power equals force parallel velocity. Can you figure out how powerful he is in this way? Okay, so this is what to do, right? You find your force. Okay, so actually I guess you can't do it unless you know that the Wookiee weighs 1,000 newtons. So it's a little Wookiee, right? But the question is that the force that he has to apply that's parallel to the velocity? No, it isn't, because the force that he has to apply is going to be sine theta. So the force he has to apply is 500. And then the velocity would be 20. And so the power would be 10,000. Okay, but let's look at it in another way. Okay, so let's say that since we have, now this is important, since we are talking about velocity and force being parallel, could I figure out what my velocity is in this direction and then use the full weight? And you reply, but yes, right? So if I'm talking about this, how many meters is this? Well, it's going to be 50. Do you agree? Okay, so if we go power is force parallel velocity, then we could say power in this case is 1,000 because the force that he's pushing that's parallel, well, he has to cancel that out. So the force that he has to push that's parallel to what we call this velocity then would be 10,000 watts. Do you agree with that? So let's look at this. Could we say that power is change in potential per time? Yep, so power would be mg, which is 1,000, h, which is again that half thing, sine 30. So it's 50, again divided by 5. And we should get the same answer. So this is all the same stuff. The reason why I did this is so you can see. Whatever you see, you can use. The two rules you have to follow, though, are either change in energy per time or force that's parallel to a velocity. Okay, hopefully that helps you complete your next assignment. Have a good day.